So let's look at some calculations involving buffers. Calculations involving buffers. So for a typical buffer, what we're typically going to give you is we're going to give you a particular acid conjugate base system. We'll give you the pKa of the acid you need to use. Okay? We'll also tell you what pH we want you to make the buffer at. If I give you both the pH and the pKa then how many unknowns are left in this equation? 2. And what we'll usually do is we'll solve for this ratio. And so your Henderson-Hasselbalch turns into A minus over HA equals 10 to the pH minus pKa power. That's what this really rearranges to. Notice we had to get rid of that log, which was a 10 to the power term. So we subtract pKa to the other side, and then 10 to the power on both sides. But even though I've rearranged this, it's still the same equation essentially, or at least it comes from the same equation. How many unknowns are in here if I know both pH and pKa? There's still 2 unknowns. If you have 2 unknowns, how many equations do you need? 2. And so here's the deal. The second equation, this one's the first one. The second equation we always use is that the concentration of A minus plus the concentration of HA is equal to your total buffer concentration. So if I want to make a 0.1 molar acetate buffer, let's say, well, notice acetate buffer would have both acetic acid and acetate in it, but we just simply call it an acetate buffer. But what that means being 0.1 molar acetate buffer is that the combination of these two, the sum of these two combined, would equal a total of 0.1. That's your second equation every time. Cool? So these are 2 equations. I want the ratio from Henderson-Hasselbalch, and then I'll use what the total buffer concentration is to get the second one. That's where we're going to go. So a couple other things we might do. So notice, what do these brackets mean? Concentration, molarity of. And what's molarity? Moles per liter. So notice A minus here, concentration of is moles of A minus over liters of solution. Concentration of HA is moles of HA over liters of solution. But it's the same solution, right? So is the liters of solution different in either case? No, so you could look at that as canceling. So moles A over liters, moles of HA over liters, the liters cancels. And what would you be left with? Just moles of A minus over moles of HA. And so sometimes it's convenient to actually do this as a ratio of moles instead of molarities, and to do a very similar equation as a sum of the moles equaling the total, not concentration, but total moles of buffer. And we'll see when that might be an easier way to go about doing this. But we'll do it both. All right, so let's look at your buffer calculations. First question says, show how to make 1 liter of a 1 molar acetate buffer of pH 5.35 using appropriate concentrations of acetic acid and sodium acetate. Cool, so we just have to use the appropriate concentrations of acetic acid and sodium acetate. So making buffers, anybody want to admit that you thought this was kind of hard? Cool. So one, we're going to ask you harder questions in a biochem class than we would have in a gen chem class anyways. But gen chem's also a distant history. So when I was a junior in my undergrad, I took a biochem lab, and the first day they told us to go make a buffer and had all the things on the counter. And there were 4 of us, and it took us an hour and a half to make a buffer. So making a buffer is not something that's just totally intuitive or something you remember from gen chem in all likelihood. So if it was hard, you're making me feel better, because it took us an hour and a half. So, but it is a necessary evil, and you want to get good at this, very proficient at doing this and doing it quickly. So in this case, we got the pH of 5.35, pKa is 4.75, and we want a total molarity of 1 molar buffer. So in this case, I'm already good to go for my 2 equations. I know everything I need to know to set these up. And so in this case, what is the ratio of A minus over HA equal? 10 to what power? 5.35 minus 4.75. What does that come out to, by the way? 0.6, right? Cool. Second equation. Second equation is concentration of A minus plus concentration of HA equals what? 1 molar total buffer concentration. So this equals 1. Sweet. Now I have 2 equations, 2 unknowns. So we're going to do a little substitution to solve for this. So in this case, what is 10 to the 0.6 power? What's 10 to the 0.6 power? I can't do it in my head. What is it? 3.98. I'm going to round it to 4 to make the math a little simpler, but if you were doing this on a test, I'd use 3.98. So, but I'm going to use 4. So this 10 to the 0.6 is 4. So A minus over HA equals 4. And from that equation, I'm really going to rearrange this a little bit and solve for A minus and say that A minus equals 4 times HA. Just going to bring HA up to the other side, multiplying by HA on both sides. And because HA equals that, because A minus equals that, and I really technically could have solved for HA as well, but A minus is just easier to solve for. I'm going to take that, and since A minus is equal to that, I'm going to substitute it in the other expression, the other equation, for A minus. And so in this case, we end up with 4 times HA plus HA equals 1 molar. Now, a lot of students see this, and they don't struggle too much with this. What's 4HA plus HA? 5HA. But for whatever reason, when there's decimals, a lot of students will see like 2.639 HA plus HA, and they don't know how to add those. So 2.639 HA plus HA would be 3.639 HA. So it's just pretend these are x's. 4x plus 1x is 5x. Same kind of thing. As long as they're whole numbers, students don't seem to struggle. But as soon as they're decimals, for whatever reason, it just seems much more difficult. So, but same thing you've been doing in algebra forever. For whatever reason, though, we have a mental block. That algebra just works out better when everything's x instead of anything else. But here, 5 times HA equals 1 molar. And so then what's the HA concentration come out to? 0.2 molar. And if HA is 0.2 molar, I can actually use either expression here. Doesn't really matter which equation I use. But if HA is 0.2 molar, then what's A minus? 0.8. So once you get 1, you just plug it back into either of the other two equations, your two original equations. There's the concentrations of HA and A minus I need to get to. If you were going to actually make this up in the lab, you'd actually take this a step further. So you'd take your concentration, moles per liter, and you'd multiply by how many liters you're making. Well, multiplying by 1 liter makes it easy. So multiply this by 1 liter, and you'd need 0.2 moles of acetic acid. And you'd need, again, multiplying by 1 liter, 0.8 moles of acetate. If it was sodium acetate, you'd have to use the molecular weight of sodium acetate and convert that 0.8 moles into grams. Measure it, weigh out those grams, and pour it in your beaker. For the acetic acid, it's a liquid. So depending on if you started with some concentrated stock solution or if you started with maybe pure acetic acid, which might be a little crazy, you might have to dilute it down to the appropriate concentration or something like that. But that's kind of the approach you'd take. But this is as far as we're going to take it here for a calculation. Cool. Any questions on this? This is the easiest of the buffer preparation calculations. We just had weak acid and conjugate base, pouring them both in directly. So if we start using weak acid and strong base, or weak base and strong acid, things are going to be a little bit more difficult here. So in case you're wondering, we will take a break here very shortly. All right, next question says, show how to make 1 liter of a 1 molar acetate buffer solution of pH 5.35 using acetic acid and 2 molar sodium hydroxide. So if you notice, this part of the question hasn't changed. We're still trying to make 1 liter of 1 molar acetate buffer, pH 5.35. The pK of acetic acid is still 4.75. This hasn't changed. For this question, you would have to do everything we've already done already, and then more. So, but since we already did this, I'm going to take advantage. But notice, this question we're on right now is a long question. We'd do all this, and then we'd have to keep going. One little extra step. So in this case, we're dealing with adding 2 molar sodium hydroxide, right? What do you know about sodium hydroxide again? Strong base. How much do strong bases react or dissociate? Completely. For reactions that are equilibrium, we deal with molarities because we want, KEQ or KC or whatever you want to call it is molarities of products over molarities of reactions. So for equilibrium reactions, we deal with molarities. But for reactions that go all the way, molarities don't help you. You need moles. I don't know how many moles of each reactant I had. That way I know who the limiting reagent is. And whenever you add NaOH or HCl, those are strong, and you better start dealing with things in moles rather than molarities. And so in this case, I got molarities here of HA and A-. I solved for that. I might have been tempted to work out the math in moles, but either way, I'm going to turn these into moles. By multiplying each of these by the 1 liter I'm trying to make, I now realize that I need 0.2 moles of HA and 0.8 moles of conjugate base, acetate in this case. That's what I need in the end. But notice, was I starting out with both of these available in this question? No. What do I have available? Only HA out of these two. And what am I adding with that HA? NaOH. Well, HA is an acid, NaOH is a strong base, and they're going to react. How much are they going to react? All the way. All the way. What will I get as products here? Sodium acetate and water. This is kind of like a titration here. Kind of like a titration. And so if you look, this titration reacts completely. And the way I'm going to treat this, I'm going to say that we're going to add X number of moles of NaOH. And the X number of moles of NaOH is going to neutralize some of the HA. How much? X amount of HA, so on and so forth. So, and in this case, once it's neutralized X amount of HA, I need to have this amount of both of these left. That's what needs to happen. So let's look at this for a minute. Let's just pretend for a minute. Let's say I started with 10 moles of HA. If I added 1 mole of NaOH, how many moles of HA would I have left? 9. How many moles of NaA would I have formed? 1. How many total moles of HA and NaA would I have at that point? 10. The total between these two is always going to be the same as however much of this you started with. If you start with only HA, so then by the time you've neutralized some, every one you neutralize turns into this. And so the combo of these two has to add up to the same number of moles you started with. Well, how many total moles of HA and A- do I need to end up with? I need to end up with 1. That means I better start with 1 mole of HA. Because whatever amount I start with, that's the total amount of weak acid conjugate base moles I'm going to have when we're done. Cool. And in this case, we didn't start with any sodium acetate. We need to make it. Cool. So assuming NaOH is our limiting reagent, and it has to be for this to make a buffer, we're going to lose all of it. How much HA are we going to lose? Same amount. It's a 1-to-1 ratio. So if I lose X amount of NaOH, I have to lose X amount of HA. And how much NaA am I going to form? Plus X. And what I know is that when I'm done, how much HA do I have to end up with? 0.2 moles. And when I'm done, how much NaA, A- in this case, do I have to end up with? What's X? 0.8. X must be 0.8. And again, we defined X as the number of moles of NaOH we needed to add into our solution. And so in this case, it was 2 molar NaOH. Notice, what's molarity? Moles over the volume in liters. If we rearrange this, we can see that the volume in liters is equal to the moles over the molarity. And in our case, we just figured out that X, the number of moles of NaOH, had to be 0.8 moles of NaOH. And what was the original molarity of the NaOH? 2 molar. And so lo and behold, the number of liters we need to use is? How many liters? So what we needed to start by putting 1 mole of acetic acid into our beaker. We needed to add 0.4 liters of 2 molar NaOH into our beaker, and then fill it up to 1 liter total. That's how we would have made this buffer. The second question, the second half of this alone is not so bad. right? Well, that's because we already finished this part from the previous question, right? But realize all of this and then all of this would have been required to come up with this answer. Big pain in the butt. Any questions? Keon.
So then at the end, the amount of the liters of NaOH plus liters of H2O and conjugate base and acid are equal to 1 liter?
Sort of. So depending on what form, again, in this case, acetic acid is a liquid. So depending on what volume we added, the key is the volumes we all add together may not add up to 1 liter exactly. So sort of. And it seems like kind of weird, but notice when things mix, the volumes often change a little bit. And so we wouldn't actually add, so many liters of this and so many liters of this and then take 1,000 milliliters and subtract it off and do the rest. What we would do is just get a 1 liter flask, put these in first, and then fill it up. So almost to 1 liter, mix it up, and then fill up the rest to 1 liter. That way, the total at the very end is 1 liter. If I would have just mixed in the appropriate number of milliliters altogether and then mixed it all up, and I might have said, oh shoot, it changed volume on mixing, and now my volume's off. So we would just fill it up to 1 liter. Cool. For dilute solutions, we can do that pretty easily and just assume it's the same. But for more concentrated solutions, maybe even like this one, that'd be a little off. Questions? Sweet. It works exactly like this, but in reverse. If we would have started out only with A minus and like a strong acid like HCl. But same type calculation, I'm actually going to skip it. There was a question on the handout, but I'm going to let you guys work that one out on your own. But it works in principle the same way. So, and for the next question that was on your handout there, I set it up with exactly the same numbers. That way you didn't have to resolve this. But instead of this titration, you'd start with A minus plus HCl forming HA and do it the other way around. Any questions? Right here.
So the HA there has the 1 mole.
Correct. This is what we start with here.
That's because you knew that you needed 1 mole at the end.
So, and that's, in this case, this is what I needed in the end, yeah. And I know I needed 1 total mole of both my buffer components together. And again, how many moles you start with here, at the end, these are going to add up to that same number. And that's why I made it 1 to start with. Cool, welcome. So the last question on that second page says, how much would the pH change if we added 10 milliliters of 1 molar HCl to the above acetate buffer at pH 5.35? So 10 milliliters of HCl. So in this case, if you added 10 milliliters of 1 molar HCl to a liter of water, the pH would go down from 7 to like 2. So it'd be a huge pH drop. But that's not a buffer, right? Pure water's not a buffer. So now we're going to try and add the same amount of HCl to a buffer, and we're going to see that the pH is not going to drop down 5 units like that. It's going to drop down a whole lot less. So look at the action of our buffer. So in this case, we're adding 10 milliliters of 1 molar HCl to our buffer. And we're just going to see, okay, then what happens? Cool. We were told that this is a buffer of pH 5.35 initially. And again, we're told all the same stuff. The pKa was 4.75 for acetic acid, all that lovely stuff. So here's the deal. This problem is not going to be very hard. But it's not going to be very hard because we already did this one. Had we not done this first, this question, I would look at it and be like, oh, stand up and you just scream out loud. So have a little tantrum in the middle of class. So it's not still the worst problem in the world, but it's definitely a lot easier because we already did this. And so here's the deal. What if we added into our buffer solution? HCl. Okay. And what is HCl? Strong acid. What do acids react with? So bases in general. And who's the base that's pretty much in our solution? In our buffer solution? Ooh, we haven't put any NaOH in there. So notice the NaOH all got neutralized in making the buffer. Notice whether we make a buffer directly from weak acid conjugate base or whether we use strong acid or base to kind of titrate it a little bit, all that gets used up and consumed in making the buffer anyways. So what base do we really have in our solution for HCl to react with? Conjugate base, the acetate ion in this case. And so in this case, the reaction we're looking at is really the A minus reacting with HCl. That's the reaction we're looking at. And again, is this, being that HCl is involved, is this equilibrium or is this going to completion? Going to completion. And in this case, we're going to form some HA and some chloride. So in this case, how many moles of A minus? Again, this is going to completion, and things that go to completion, we need moles, not molarities. So how many moles of A minus are in our solution? Well, let's go back. A minus and HA, that's the concentrations we needed to end up with. And if it was a 1 liter solution, then how many moles of A minus are in there? 0.8. 0.8 moles per liter times 1 liter is still 0.8 moles. And so that's what we start with here. How many moles of HA did we have in our buffer solution? 0.2. Notice if we'd had any other volume than 1 liter, we would have had different numbers here than our molarities. Cool. And how many moles of HCl have we added here? Well, it's 1 mole per liter. How many liters is that? 0.01 mole, or 0.01 liters. And so 1 mole per liter times 0.01 liters would be 0.01 moles. That's what we've just mixed together. That's what we've just mixed together. So again, this question, if I just asked this question without asking the previous ones, we would have first had to calculate it out based on the initial pH of 5.35 and the pK of 4.75 and the total buffer concentration of 1 molar. We would have to initially figure out what these initial concentrations were to come up with these initial number of moles in our buffer. And once we've done that, now we can see how the HCl is going to change that. So who's my limiting reagent here between the acid and base reacting? Definitely the acid, so I lose all of it. So I lose the same amount of A minus, they react 1-to-1, and gain the same amount of HA. And so in this case, 0.8 minus 0.01 is 0.79. No HCl left, it's all gone. So here, 0.21. Cool. And so when the dust settles, when the HCl is all used up, that's what's left in my buffer solution. Is it still a buffer? Yeah, I still got a fair amount of both these guys. If either one of these was gone, I wouldn't have a buffer anymore, but this is still a buffer. And I mean, technically, these have to be within a 10-to-1 ratio to be in that kind of range, but we're good. So in this case, what do we do to get the pH of a buffer? Yeah, we use Henderson-Hasselbalch still. And there's our Henderson-Hasselbalch. But if you recall, I said sometimes instead of using molarities with Henderson-Hasselbalch, we can assume the liters, when we do this as moles per liter over moles per liter, it's the same solution, and so the liters cancel. And you can just look at this as a ratio of moles. Now notice, moles of A minus does not necessarily equal molarity of A minus for every solution. That's not necessarily true. But as a ratio, the ratio of molarities will always equal the ratio of moles. And that's actually the version I'm going to use in our example here. Instead of molarities, I'm going to use moles of A minus over moles of HA. Cool. And in this case, what's our pKa? And so in this case, if you look, how would I have, if I was given this buffer instead, if I had been given the original buffer that had 0.8 moles of A minus and 0.2 moles of HA, how would I have found the pH of the original buffer? Well, I could have just plugged in 0.8 and 0.2 and be done with it, right? And that pH would have come out to 5.35. So if you're asked to find the pH of a buffer, you can pretty quickly find the pH of a buffer. So in this case, wasn't the question we asked, but just want to show you the quick way of doing these kind of calculations of buffer pH changes. In this case, how many moles of HCl did we add? 0.01 moles, right? And so in this case, it neutralizes the A minus, and we lose 0.01 moles of A minus. But when you neutralize 0.01 moles of A minus, what does it turn into? 0.01 moles of HA, and that's why it's added right there. And so I've set this lovely table up for you to see where these numbers came from. But I often recommend, if you can get there conceptually, just going straight to Henderson-Hasselbalch. Plug in the initial values. If you've added strong acid, well, that's going to neutralize base. You subtract there, add on bottom. If we'd have added NaOH instead, then we'd have subtracted from the acid, because that's what gets neutralized, and added on top. Just been the reverse. Cool. Anybody get me an answer for this? What does this come out to? What is it? So how much did our pH change? 0.02. From 5.35 initially down to 5.33. It only changed 0.02. Our buffer did an excellent job.